talk about today are a number of issues related to geospatial applications of artificial intelligence. I'm going to raise a number of questions and not necessarily provide much in the way of answers, but I'd encourage you to think that what I'll be talking about is the issues that you should be concerned with when you are using geospatial applications of AI. And this is a very rapidly developing field, and there are many, many issues that really need to be considered in this connection. I want to talk about 4 particular topics. All of them are an important part of what I'll be saying, and all of them intersect to some degree. So I'll certainly be talking about geospatial. I'll be talking about analytics, particularly advanced analytics. I'll be talking about artificial intelligence and deep learning, and I'll be talking about big data. And really, I'll be talking about the intersection of all those 4 ideas, 4 areas. So I want to focus particularly on use cases, and that's why I chose the title that I did. What are we looking for? What are the applications? What are the questions we're trying to address in using these technologies? So this is a focus on what you might call use cases or applications, usage of these tools and technologies. And by way of background, I want to make this point about geospatial technology and its roots. Geospatial technology originated in maps and remote sensing. And in that sense, it's a set of hammers, a set of tools in search of application. Because there are many, many applications of maps and remote sensing. And ever since geospatial technology began in the mid-1960s, there has been a search for useful applications. And what we're talking about today and in this workshop is simply the continuation of that set of practices. But it's important to recognize that early on, the costs of making maps and remote sensing, costs of GIS were very high. And so it was necessary to create as many uses as possible to justify those high costs. The focus was on 2 dimensions, not 3. And the focus was on making the data valid for as long as possible in order to justify the costs. So inevitably, there was an emphasis on representing things that were static. Maps tend to represent topography, streets, rivers, lakes, things that stay static, and not to represent movements, flows, the actual locations of individual people. All of these things are too dynamic to justify the very high cost of mapping. And the point I want to make is that our current practices are still influenced by this legacy. These arrangements that we've made over the last 50 years are still influencing how we go about using GIS and remote sensing. And I want you to keep that point in mind as we go through this. To what extent are the practices that we still use influenced by that legacy? And there'll be several points where I think this question becomes extremely important. That's been something that has concerned me a great deal. I've been in this field now for 50 years, more than 50 years, and I'm very well aware of how things have changed. but also how practices persist, how we still think essentially in 2D, even though today much of our technology is 2D. So we are today facing essentially a new world, which costs have declined dramatically, in some cases effectively to zero. Effectively, it costs nothing today to make a map. It costs nothing to acquire the data necessary to make a map. And so today we can design tools for specific uses, for a single user, for a single moment in time, for a single application. This is then very different from the world of 20 years ago, even 10 years ago. It's a world in which the cost of what we do declined almost to zero. So let's ask this question, now what kind of uses are there? And what uses will intersect these four? And in doing so, I'm suggesting we start not with the hammer, but with the nails, the applications, with the uses. And yet, if you look at today's GIS and today's image processing software, still the user interface presents a list of functions rather than a list of potential questions. And the user interface of Esri's ArcGIS Pro, for example, contains several thousand possible functions. And it is left almost entirely to the user to decide which of those functions to use in what sequence in order to address a question. However, I said that the number of functions is in the thousands. If you are working in a given application domain, such as forestry or agriculture, the set of questions you're going to ask is much less than that. It may be as little as 10. In agriculture, for example, it's easy to list the 10 most popular questions that people tend to ask of geospatial technology. And that is very much less than a set of functions. So what I'm arguing for is a user interface, a user experience, which begins with questions and uses the power of the machine, the power of artificial intelligence, to translate those questions into workflows, into sequences of functions. And that's something that we have not yet done. Back again to the legacy. Our legacy is to focus on the functions rather than on the questions. So here's an example, because I'm talking rather abstractly. Let's focus for a moment on the soil map, which is an important kind of data for many applications in agriculture. And the soil map, if you think about it technically, is what we call an area class map. It maps irregular areas denoting uniform soil type. And it includes lengthy descriptions of type. It's made by highly trained experts. And there is an assumption of replicability. But in practice, two highly trained experts asked to make a soil map of the same area would not produce the same map. In other words, this process is not replicable. It's based on sample points. It's based on interpolation from ground observation and aerial photography. As a result, every point in the map is assigned to a single class. And so, in effect, this is a mapping from location X, class C. And here's an illustration. In the middle, I have a typical soil map, and you can see the lines surrounding areas of equal class. It's superimposed on an image, an orthophoto quad. But think on the left-hand side, all the different inputs of information which went into making that map. So the expert who made the map brought together 7 different kinds of knowledge to create that map. And on the right-hand side are 6 possible applications. Again, applications of the map. And my point has been that in order to afford the cost of making the map, it was necessary to find as many applications as possible. And there's a very simple principle there. If you had only one application in mind, you would do better. You would make a better map. But the maps are compromised and to cover as many applications as possible because of the high cost. So if we look at this today, trying to escape the legacy, what we might do is identify a particular application and the particular inputs which would answer that question and avoid the map entirely. So for example, if in my garden I want to grow spinach, if I went to this map, the soil map, I would find it is far too coarse to satisfy my question. My garden is very small on the scale of that map. What instead I would do is access historical records of crop performance, perhaps talk to my neighbors, and think about the particular needs of spinach. The general purpose soil map would be of no interest and no use. And that's the modern view. It focuses on use cases and it focuses on specific products to satisfy those use cases. Because the old argument that supported this single map is no longer valid. So with that introduction, I want to talk a little bit about a specific case of terrain modeling. This is a particular kind of geospatial data. And I want to make some points about representation and particularly representation of terrain. And then I'll use this introduction to talk a bit about the use of artificial intelligence in a particular application. So in modeling terrain in GIS, we typically have 3 models that we use. The first, the digital elevation model, which represents terrain as a raster of spot heights. Secondly, the triangular mesh or TIN, which represents the terrain as a set of triangular facets, each of uniform slope. And then the third, digitizing the contours from a topographic, a DLG or digital line graph. So here is the digital elevation model, the raster, and superimposed on that is hydrography, the streams and rivers. So you can see elevation is simply represented as a raster. Here is the triangular irregular network. And you can see that on the right-hand side, the great advantage of the TIN model is that we can use more triangles in areas of steep, rugged terrain and fewer triangles in the flat areas of the valleys. So it's very economical in the sense that it spreads data unevenly across the surface of the earth. And then here's the contour map. We simply digitize each of these lines. So we have 3 different representations. And the question you might well ask then is which model is best for which use? And there are uses for which the DEM is best, uses for which the TIN model is best, and uses for which the DLG is best. So for example, which model would you use if the topography consisted of rounded hills and U-shaped valleys? In other words, it was glaciated terrain. A very common type of terrain in the north-central United States. Which model would you use? And clearly you would not use triangles because you don't have triangles separated by sharp ridges, valleys. In fact, you might use DEM, or you might use digitized contours. Or if the terrain was sharp ridges and V-shaped valleys, then definitely you would want to use the TIN model. But you would have to be careful to make sure that the edges of the triangles matched the bottoms of the valleys, the tops of the ridges. In other words, it wouldn't do to randomly allocate triangles across the surface. And then if your task was to represent canyons, which are dominated by horizontal bedding and vertical cliffs, again, which of those three models would be best to use? The point I'm making then is that in geospatial technology, we always have multiple ways of representing the world. And we do best when we match those methods to the specific uses. Which method is best for which use? Here's another issue which confronts us in using digital elevation data. These are histograms of elevation. So the x-axes are intervals of elevation in meters, and the vertical axis is percent of points at that elevation. The upper graph, these are both from an area of Guatemala, the Petén state in Guatemala. The upper graph, the upper histogram, is from the Shuttle Radar Topography Mission, SRTM, which is a sampling at, in this case, 90 meters, creating a raster DEM. And you can see very much as you would expect, there's quite a lot of land around 60 to 80 meters. It's quite a lot of land around 150 meters, and then things tail off in both directions. The second is the kind of data that you might get from the government of Guatemala, and it's official government data. And you notice something very strange here, that there are very sharp peaks, lots and lots of cells in the DEM at 60 meters, 80 meters, 100 meters, 120, 140, and then fewer points, spikes in between at the 10-meter interval. And you might ask yourself, what has happened here? Is this real? And the answer is no. This is an artifact of how these data were created. They were created by digitizing contours and then interpolating from the contours to a regular grid. And what tends to happen in that kind of method is that you either end up with too many points at the contour elevations or too few. In this case, far too many. So this is a failure of the production process. It has nothing to do with the landscape itself. So let me try to summarize this in a series of issues. And remember that each of these points is going to apply not only to this type of geospatial data, but to all types of geospatial data. So number one, some terrain types are better represented using specific models. Or if you want to think more generally, some types of phenomena are better represented using specific models or specific purposes. The choice of model is also related to the eventual use. Which model is most fit for which application? And all representations of terrain are uncertain, and some of the uncertainty results from the method of compilation, from the interpolation process that was used for the Guatemala data. A further issue is this, the semantic issue, because we might have to ask, what does elevation mean in each of these cases? And if we were to think about elevation, let's say for a DEM, a raster, we might ask the question, what elevation has actually been captured? And there's a choice here, because sometimes what's captured is what we call the bare earth surface. In other words, a surface after trees, after the buildings have been removed. Or some of these methods will produce essentially the top of the tree canopy. That's true, for example, of SRTM if the canopy is dense. Other elevations might represent the tops of buildings. So we have an important distinction here between what is called a digital terrain model and a digital surface model. This is, of course, part of the provenance of the data. It's an essential question to ask whenever this type of data is being used. So just to generalize this, any geospatial data will need information about how it was created and what it represents. Simply to say, I have elevation, is never enough. There are many different meanings of elevation, many different semantic of that very simple word. We might also ask, what elevation is assigned to each grid square? Is it the elevation of the central point of the grid square? Or is it a mean over the grid square? Or is it some other convolution? And again, this is an important part of the provenance of the data. And more issues. This one, I think, is often overlooked, and for reasons which I'll explain later. The point here is that vertical errors with GPS are typically greater than horizontal errors. And the reason for this lies in the difficulty of defining a vertical datum. What is zero for elevation? For India, for example, the mean sea level on the Bay of Bengal is substantially different from the mean sea level off Mumbai. And that sort of issue is pervasive around the world. So there are additional uncertainties in GPS for the vertical errors compared to the horizontal errors. And then lastly, and here's perhaps the most important point of all, the errors in any data such as a digital elevation model are correlated in space. And the correlation is a positive spatial autocorrelation. If they weren't, it would be impossible to derive useful measures, derivative measures of things like slope, aspect, or curvature. If you think about what's happening here, let's suppose, and this is quite typical, that a digital elevation model has a 5-meter vertical error. If that meant that every cell was independently raised or lowered by at least 5 meters, then estimates of slope would be horrendously unreliable. It's only because they are correlated in space, nearby cells tend to have very similar errors, that we can estimate slope or aspect at all. So that introduces something I want to spend a little bit of time on this morning or this evening, which is this problem of uncertainty. And I want to specifically talk about uncertainty as it relates to artificial intelligence, use of AI, machine learning with geospatial data. Here's an illustration of the significance of uncertainty. This is topographic data from the US Geological Survey. It's an area of Pennsylvania. What I've done is emphasize the 350-meter contour. The data has a 20-meter contour interval, and you may be able to see clearly some of the other contours. But the sharp line you're looking at, the heavy line, is the 350-meter contour. Now that map says nothing about uncertainty. It pretends that we know at least as much about the location of the 350-meter contour to draw it with that thin, bold line. Let's suppose instead that we admit, and this is a reasonable assumption, we admit that there is a 6-meter root mean square error in the vertical. Then we can calculate the uncertainty position of the 350-meter contour, and here it is. So with 95% confidence, we know that the 350-meter contour truly lies somewhere in that colored area. But exactly where, we do not know. And as I say, that's a reasonable assumption based on what we know about this data. So what it's saying is that the actual uncertainty in a lot of geospatial data is surprisingly large. We create maps deliberately to make the world look simpler than it is, in effect, to hide uncertainty. Maps typically show nothing of uncertainty. Yet when we try to show it, it turns out to be surprisingly large and, in effect, quite unsettling. Here's another example. This is from near the University of California, Santa Barbara campus. These are 7 commercially available data sets of street center lines. This is the intersection of US Highway 101, that's across the middle, and State of California 217, which goes down to the left. And notice how different these are. Each of these 7 versions substantially offsets what it's saying about location. Are things really this bad? Yes, this is really quite typical. We escape this because we rarely see 2 independent data sets superimposed. When they do, the result is quite scary. But notice a very important point here, that even though the positions have been distorted, these are not independent locations subject to error. The entire street has been displaced. And once again, there are strong spatial correlations, autocorrelations in the errors. So that in spite of substantial errors, the shape of the street is actually maintained, even though the street has been shifted quite substantially. None of these is in fact the truth. And if we were to try to deal with, let's say in this case, 2 data sets, try to remove the differences, we could do that by a simple arbitrary technique. We could remove them, but neither of them is the truth. And there is, of course, no guarantee that the result of merging them is the truth either. We simply give one of them priority or give both of them equal weight. So what does all this mean for AI? And how can we approach AI with uncertain data? And specifically the kinds of uncertainty that geospatial data show when all geospatial data are uncertain. Every geospatial data set has some degree of uncertainty. The important question is not whether the geospatial are the truth. The important question is whether the geospatial data are fit for a specific use. And all of this, of course, is given the special nature of uncertainty for geospatial data, which is this point about spatial dependence. So, use cases. And here are some possible use cases. I want to use terrain in the next few minutes to illustrate the use of AI. Buildings, forests, mines and caves, all of these have been used as examples of applications of AI. Here, for example, is a very nice exercise which produced a LiDAR point cloud of the Carlsbad Cavern National Park, New Mexico. Notice something very interesting in the ceiling. Those stalactites, not vertical, because the rock on which they have been formed has shifted since they were laid down. So they now hang out of the vertical. So here are some uses involving AI. And I want to talk specifically about one, which is the find similar use case. So the find similar use case, a very popular tool in marketing, where you might, for example, have a given restaurant which was doing particularly well and search for similar locations for another restaurant. Find similar. We might try to find hotels that are similar. And these are particularly responses to the advent of big data, because lots and lots and lots of data are now available. They specifically exploit the power of artificial intelligence to learn and classify. So find similar is an excellent example of the use of AI in geospatial applications. So I want to talk about the work of Wenwen Lee, who is a professor at Arizona State University, and it uses convolutional neural nets as a technique of deep learning and classification. It's applied to the problem of finding craters on the Earth's surface and potentially on other planets. So it's an example of using AI to address geospatial questions, or what we might call geo-AI. So this is the crater detection case. Here are some craters, photographs of real craters on the Earth's surface. And what we'll be trying to do is to search other craters using something rather similar to facial recognition technology. So this is find similar. And notice there are questions concerned with craters inside craters and craters that overlap, which will have to be dealt with as special cases. One of the advantages of this technique is that it's possible to search for features, compare features in very different environments. So craters, for example, that are partially covered by forests, or craters that have been glaciated. And here's a reference to a paper derived from this work, automated terrain feature identification from remote sensing using deep learning. It's possible to use a very similar technique for many other kinds of features. So Professor Lee has also worked on some of the features associated with permafrost in high latitudes. Pingo, for example, which is a spectacular feature of permafrost landscapes. And it's possible to think of how this technique could be used in search and rescue operations. We could imagine, for example, a case where a group was lost, had no access to geospatial technology, was able to describe their surroundings, and we used AI to find a suitable location, the most likely location, based on the description. And another application of this, which I was briefly involved in, is a project called Finder, which was funded by the Office of the Director of National Intelligence in the US. And the task here was to identify where in the world photographs were taken. These might be photographs or videos. They would be taken at ground level, but using any type of camera, any season, any time of day, any weather conditions. It was important to be accurate and important to do this quickly. And I'd like to just show you a few examples. I like this problem very much because it is a very geographical problem. But let's try you on this one. Where was this photograph taken? And there are websites already that you can access that you can send a photograph to, and they will attempt to resolve that question using and in this case, you will find about a 40% chance that this photograph was taken in Australia. And what's indicative here, particularly, is the large expanse of blue sky and the large expanse of bare dirt, street. And those are key attributes associated with photographs from Australia. If you were a bit cleverer, you might read that street sign on the middle right, which says that is Sturt Street. And if you Googled Sturt, you would find Sturt was an explorer of early Australia. Many towns and cities in Australia have a Sturt Street. And you might also recognize that there are 6 out of 7 vehicles in the image which are white. You might know that it's very common in Central Australia for vehicles to be colored white. You can narrow this down quite quickly. This is, in fact, taken in Silverton, New South Wales. And you can do that using a variety of sources that we now have available. In other words, this is the kind of question answered by GeoAI. Here's another one. Where was this photograph taken? And you'll quickly recognize that any kind of readable script is a very good indicator. There are a couple of business names readable in this image, and if you Google them, in less than a second, you will find this photograph was taken in Porto Alegre in Brazil. But this one is far more difficult. What techniques would you use? What data sets would you use to try to determine whether this photograph was taken? A very interesting challenge. And there are all sorts of clues, including the angle of the sun, topography, the presence of a tree over here, would be indicators that would help you. And hopefully you would eventually determine that this photograph was taken in Namibia, about 300 kilometers from the coast. One of the issues that I'm very concerned about with geospatial data, and I've already referred to it in connection with the soil map example, is what's called the replication crisis. This is something that's received a lot of attention in science in the past little while, and it amounts to essentially a failure to replicate previously published studies. This became a real issue about 20 years ago in psychology, and it's since spread to large areas of science, including the geospatial area. It relates also to the practice of scientific reporting, because one of the things one learns very early on as a scientist is that it is necessary to report sufficient detail to allow someone else to reproduce the results. And that criterion has become more and more difficult to impose these days. Replication and replicability is a problem that is growing worse as science gets more complex. As people rely on data which are not published, data without metadata or provenance, so data that people essentially don't know enough about, proprietary software that investigators didn't write. Think about this in the context of machine learning. How would you publish sufficient information to allow someone else to repeat and replicate your machine learning? And it's also a growing problem because of poor documentation for software and workflows. It's easy to criticize, for example, many sources of GIS data for not describing software in sufficient detail. Things are getting better. So we have tools like this. This is Esri's model builder, which allows you to capture and store and replicate and share the workflow of particular analysis. And there are things coming such as Python Jupyter notebooks, for example, which have a similar kind of approach. But I want to use this example because I want to make the point that replicability has a particular meaning in the geospatial world. So we've already seen how uncertainty has a special meaning in the geospatial world. Here's replicability. This is the state of Mississippi, highlighted here. And these are the counties of the state of Mississippi. And I've presented a scatter plot of two variables. The x-axis is percent African American or black, percentage of the population of that county who are African American. And the vertical axis is median value of housing. And you can see what's evidently a negative relationship. The counties with a higher percent African American have a lower median value of housing. So you might say, we've discovered something interesting. You might publish a paper in which we conclude that median value of housing is negatively related to percent black. But making that general statement would be entirely unwarranted if, for example, we switch to California and the 58 counties of California and the same two variable, because now the negative relationship has disappeared, and what has appeared instead is a positive relationship. The counties of California with a higher percent black are actually more expensive in their housing, and the tendency is for the whiter counties to be less expensive. And that's a direct contradiction to the previous conclusion. So what do we do here? What do we do? How do we generalize geographic data? What does it mean to be replicable in space? And this has been a long-standing debate in the geospatial world. The geographer Schaefer believed that the purpose of geospatial analysis should be to search for principles that apply everywhere, at all times. Hartshorne, another geographer, argued that all places are unique and we cannot generalize across space. If you apply machine learning to one district in India, you are not allowed to assume that the results of that machine learning apply to other districts in India. That's a long-standing debate. But what we have now is perhaps a compromise between those two positions, what we might call place-based analysis. And the point is here that we may be able to generalize with a single model if we allow its parameters to vary. Geographically weighted regression is a well-known technique for that purpose. And so are local indicators of spatial association, or LISA. These are techniques which assume there's a single model, but recalibrate the model, allow it to vary. Keep the variables the same, but allow the parameters to vary. So what does replicability mean then in GIS, geospatial technology? Not in the normal scientific sense, but instead, let's call it weak replicability. The same variables, the same mathematical model, but varying parameters. What we might call then place-based analysis. Example, geographically weighted regression. Here's an excellent textbook introducing GWR. There is abundant software. Esri has GWR software. R has GWR software. Many other sources of software. Here it is applied to China, and you can see that the parameters now are varying across China. Rather than fitting a single model to all of China, we allow the parameters of the model to vary. So what does this imply for AI? One thing it implies is that the bounds of study are always important. If you anticipate uniformity within bounds, then you must accept that the results will depend explicitly on the bounds. Change the bounds of a study, and you will change the results. How then do you compare one area to another? Through perhaps weak generalizability. One model, varying parameters. I want to finish this and have a few minutes for questions with this one last point. which really summarizes a lot of what I've been saying. And that's the very simple quotation or mantra: a map is not the territory. The map is not the territory. This is often attributed to Alfred Korzybski, 1933. And the illustration simply shows somebody holding a map in front of the real landscape. And it makes the point that the map does not represent everything about the landscape. It's a selective representation. What does that mean? It means that our databases in GIS always have uncertainty. They're never the truth. The relationship between the database and the real world is something that the database cannot tell you. You can only know that by knowing the real world. So maps are representations. All maps in geospatial databases leave the user uncertain to some degree about the true nature of the world. Techniques for capturing that uncertainty in metadata are generally problematic, given the special nature of geospatial uncertainty. And visualizing uncertainty is difficult. Much of the research that we've conducted shows that the best approach to visualizing uncertainty with geospatial data is through animation, through cycles of alternative realizations of a stochastic problem. That brings me to what's often called the fourth paradigm, which is a very fundamental point about data science, particularly data-driven science. It says, let the data speak for themselves. And I hope by this point I've convinced you that if you let the data speak for themselves, they do not necessarily speak for geography. Geospatial data are never geography. They're never the truth. It's impossible to measure location perfectly. All geospatial data are subject to uncertainties of various kinds. Some are not replicable. I used the example of the soil map. They're generalized, abstracted, synthesized, and detail is always truncated. So when the data speak for themselves, they do not always speak for geography. This is something that anyone working with geospatial data must always bear in mind. So I want to leave you with this. This is a very famous work of Johannes Vermeer, painted in 1668 to 1669. And it's titled The Geographer, and it hangs in the Art Museum in Frankfurt. And if you ever have a chance to get out of the airport, visit Frankfurt, I heartily recommend going to see this painting. It shows the geographer surrounded by globes and maps, with maps in front of him. So think of that as the GIS user. He holds a pair of dividers. Think of that as the equivalent of GIS functions. But the key point here is that the geographer is looking out of the window. The geographer is not looking at the map. There is some evidence that when Vermeer originally planned this painting, he had the geographer looking at the map, later changed his mind. And Roger Downs of Penn State University has written a paper about this, in which he makes the point that it is necessary to know the real world, to look out the window, in order to make effective use of geospatial databases. Because we never know what is uncertain about the data, how the data relate to the real world. So I just want to leave you with that point, because in many ways it summarizes what I've been saying. It raises, as I said at the outset, it raises issues which I think will have to be dealt with by anyone working in GeoAI. What do you make of the data? Are you letting the data speak for themselves, or are you letting the data speak for geography and speak for the truth and speak for scientific reality? So these are important questions, and I hope in leaving them with you, I produce some interest. And perhaps you have some questions or things you would like me to clarify in the last few minutes.
How does the mean sea level is being standardized? because a lot of the times, basically the river gets controls the sedimentation that is happening near the coast. So with
Yep.
all the dams getting built up, or sometimes the dams getting broken down, it controls the topography there. So
Yep.
what is the approach that is used for standardizing it?
Yep. It varies around the world and it varies country by country. So India will have its vertical datum and it will have its own procedure for determining that vertical datum. This is one of the reasons why measuring sea level rise is so difficult, because a very small rise in sea level, which is the sort of thing that's already happened as a result of global climate change, may be nevertheless difficult to measure because of the difficulties of measuring sea level. As I said, the problems over the vertical datum don't essentially matter very much when you're concerned with relative elevation, as we are, for example, if we measure slope. So the fact that Everest is, 8,400 meters high, that fact is not in itself very significant. Every GIS application would do something with it like compute slope or compute curvature or compute aspect. And because every point inherits errors in the vertical datum, those all cancel out when you measure slope or aspect. So we tend to downplay the significance of the vertical datum, because even though it is difficult to measure, it's nevertheless of remarkably little importance in actual GIS applications.
Yeah. Good evening, sir. It's an honor to be interacting with you. My question is, you just touched upon the aspects of uncertainty and replicability. Keeping this as
Yes.
a benchmark, what is your take on the booming field of driverless car technology, which basically uses LiDAR as a key component of it?
Yes. Yeah. I think we have to distinguish two kinds of data for driverless vehicles. There's the kind of data collected by the vehicle, by its sensors, and that includes the LiDAR. And then there's the type of data that is transmitted to the vehicle by a central store. And in planning a route, for example, that uses the central data. It uses data downloaded, as you do with your smartphone when you use a smartphone for guidance. You use the central data for that. But you use your eyes, and the vehicle uses its LiDAR for very short distance mapping. So when the vehicle, for example, needs to know where it is in relation to the lane markings on the street, and I apologize, I'm using an example here which doesn't work very well in Indian cities, but when you use the lane markings in the street, those are sensed by the vehicle. And so it's not necessary for the central store to know where the lane markings are. Those don't need to come from the central store, they come from the vehicle. So what is needed for autonomous vehicles is a clear sense of the distinction between what is sensed by the vehicle and what is obtained from the central store. The central store needs to tell the vehicle where the filling station is when the vehicle runs out of petrol, but the vehicle, after knowing roughly where the filling station is, then relies on its LiDAR and its cameras to actually navigate into the filling station. So filling station positioning, when you position your vehicle to fuel it, you have to position it to better than a decimeter. But there's no need for the central store to know where things are a decimeter. So that distinction is really critical, and it's really important in the whole acquisition of data for autonomous vehicles.
Hi, good morning from our side.
Good morning.
Uh,
Good evening.
my question, I'm asking two questions. Earlier, I work modular terrain model by using modular GIS environment, terrain analysis, ARDAS, and also ArcGIS. But now my field has been changed. I am now working for the rainfall precipitation. I have to calculate the average aerial precipitation for my area of interest is for district or for any river basin. Which method I have to use for isoidal technique? Because I am using isoidal technique. There are two types of technique we are using, topo to raster and IDW. But IDW is giving result not smoother than the topo to raster. First question, which technique I have to use, the IDW or topo to raster?
Yeah, I think that the point I was making about different methods needing to match the use case is particularly important for spatial interpolation because we have so many choices. We have IDW, we have many, many forms of geostatistics of kriging. We have bilinear interpolation, and we have the kind of interpolation that I already talked about, which was used on the contours to create a digital elevation model. Many, many different types of interpolation. Which one to choose? And that's a very, very difficult question. I think that if possible, I would always recommend using kriging geostatistical methods because those methods learn from the data before making estimates. Whereas IDW, you can apply to any data set and it uses exactly the same method. It doesn't learn from the data. And the same is true for bilinear interpolation, and the same is true for contour to grid interpolation. So if you can, I would suggest using kriging. However, at the same time, kriging requires much greater intelligence and experience on the part of the researcher. So it is so tempting to just use IDW, which doesn't require you to do anything. So that's my point. Right?
Problem is that IDW is not giving smoother contour by ISO height, but topo to raster is giving the smoother. So that's why we are using the topo to raster. Second question, for preparing elevation model or for generating contour, your terrain is fixed. But for my case, today's rainfall for the design storm or any storm is 300 millimeter, and day after tomorrow or tomorrow it may be 150 millimeter. But for generating contour, your interval is fixed, either 10 meter or 20 meter according to your hilly terrain or according to your plain. But for my case, the precipitation is not fixed because precipitation again varies. So what interval I have to give the equal interval, or how many sub interval I may put for that?
Yeah, I think that's a matter of the user and the satisfaction of the user. I think many of these choices come down eventually to satisfying the user. And there are many techniques in GIS which, if you had to defend them on a theoretical basis or a pure scientific basis, you'd have difficulty. But they are undoubtedly good at satisfying the user. A user, for example, our experience is that users like fuzzy maps with fuzzy classification. That, on the other hand, if you try to make a logical, rational, theoretical argument, becomes very difficult. So I would say, to answer your question, use whatever interval you find easiest to work with when you've created the map. I mean, maps in many ways are devices to create perceptions, to create impressions. And if they do that well, that's great. and I'd much rather do it well from a cartographic perspective than try to create a theoretical defense. I hope that really addressed the question you were asking.
Good morning, sir.
Good morning.
Yeah, my question is, how do you decide number of sample point recur with respect to scale of a map and RMSC, and the distribution of sample points for generating a thematic map? Yeah.
Yeah, very interesting question. There are many techniques for sampling and many ways of collecting samples. Some of the work that I've done has been in the area of adaptive sampling, which recognizes that sampling in certain areas is quite problematic because of access. So it's often easy to access locations that are close to roads, or easy to access by walking. Much more difficult to access, for example, a point in the middle of a field. And adaptive sampling recognizes that by saying that you take with you a device, and as you sample, you enter the data, and then you use the device to address the question, where would I best take the next sample? Where would the next sample most reduce my uncertainty? And you can build in, for example, measures of how difficult it is to get to that point. I want to take my next sample somewhere that reduces my uncertainty, at the same time is easy to get to. So this is adaptive sampling. It's sampling in the field, doing it dynamically, where the sampling pattern is not set in advance, but responds as the information is collected. That kind of thing, I think, makes a lot of sense in a lot of geospatial work, where you sample based on, it's a progressive, adaptive sampling scheme. And I'd rather recommend that if it's possible than some arbitrary scheme, random scheme. I think another issue that's relevant here is that there are many types of GIS application where what we start with, the data we start with, are in fact everything. We have a complete soil map or a complete topographic map. And sampling is used perhaps only to reduce the workload. But as computer power becomes less and less expensive, it becomes more and more possible simply to sample everything, analyze everything if you can. So I would suggest sampling, yes, when it's necessary to conduct a field campaign, actually collect data in the field, where the cost is directly related to how many samples you have to collect. But sampling just for the purposes of reducing the volume of data, no, I think I would try not to do that.
Yes, sir. And sir, we are enlightened by your fantastic presentation. I am the urban planner. I just have one small query. Uncertainty is always associated with the geospatial data. Replicability is also not possible. Various models we have used for the various terrains and various purpose. Then what is the future of the GIS in the smart planning, in the smart urban planning? What is your perspective regarding the future of GIS, particularly for the town planning and the city planning part?
Yeah. Smart planning has to be geospatial. So almost everything you would want to do in the way of developing smart cities, smart planning, requires a geospatial approach. So that right away says GIS. Where are the applications best? I think they come in whenever you think about the city at a great level of detail. Today, it's possible to develop transportation plans based on not summary statistics, not aggregated statistics, but actual individual tracks. We know, for example, we can track every taxi, we can track every Uber, we can track people from their smartphones. So we can work at the individual level. And this makes the task of urban planning even more geospatial than it ever was before. I'm also a great fan of geodesign, which is the use of GIS technology in design. And I think the kinds of tools that have been developed recently, I'm thinking particularly of the geodesign tools that Esri is producing, City Engine, and related tools. These are tremendous tools for urban planning. And of course, they're completely geospatial. So I'm currently editing a book. It's titled Urban Informatics, and it consists of about 50 chapters on various aspects of geospatial planning in an urban environment. And its emphasis is on the tools and the data. And that should be out sometime later this year. And I think it will do a wonderful 50-chapter job of answering your question.
Thank you, Mike. But before I let you go, I have one question. You started off saying about hammer and nails, hammer trying to find nails. Do you really think that the scene is changing and now the nails are really going to decide which hammer to use? Do you think that's happening?
Absolutely. I think that this idea of inverting the user interface so that it focuses on the questions and not on the functions is something that's now well advanced in the way Esri is thinking and the way other GIS producers are thinking. Yes, I think that about 3 years ago, I attended a session at the Esri User Conference, and the center point of that presentation was a table. And across the top of the table were functions, and down the columns of the table were questions. And this table was presented to try to help the user understand what functions would answer what questions. And my question was, why are we looking at this table? Why isn't this table inside the GIS? Why doesn't the GIS know about this table? In other words, why don't we enter the GIS using the questions rather than the functions? I think this process now is fairly well advanced, and we'll see more and more of it as time goes on.
Thank you. Thank you very much, Michael Goodchild. Let's give him a big round of applause. Thanks a lot, Michael.